Okay, so let's start chapter 2. So chapter 2 is about sampling, standardization, and calibration. So it just tells us the correct methods when we are going to do chemical analysis. No? Okay, so because depending on the situation, or depending on the situation of your analysis of your sample, there is a um, certain measures that has to be considered now so that you will come up with a good result. Okay, by the way, if someone of you is in Bicol region, stay safe, no, there is an earthquake there. Okay, anyway, so let's proceed now. So when we are doing chemical analysis, we should be able to know how to how to get samples, right? Okay, so when we say samples or sampling in general, it is a process in which you collect a small portion of your data from the population. Okay, for example, in surveys, you don't interview all of the people, diba? So for example, in Pulse Asia surveys, they do not interview the 100 million Filipinos when doing interview. They only get few portions of that population, and that's sampling. Okay, so in chemical analysis, you do not also have to get the entire sample. For example, if you are analyzing the Pasig River, you do not have to get the entire volume of the liquid in there. Okay, so you just have to get a few portion of that liquid and you bring it in the laboratory, and that's sampling. Okay, so sampling is getting a uh, representative part of the entire population. Okay, so that's there are many factors that has to be considered when choosing analytical methods. No? Okay, so depending on the amount of your sample and on the concentration of your analyte, there is a corresponding analytical method for that. No? So if you are going to consider sample size, there are four types of analysis that can be done. Considering the amount of your sample nga, no? So the first type would be the macro analysis. Macro analysis is a form of analysis that can be done when your sample size is big. No? So when we say big, that is anything greater than zero point 0.1 grams or zero point 0.1 ml. Okay, so that's macro analysis. So, macro analysis may involve the use of classical methods of analytical chemistry, such as gravimetry and titrimetry. No? Okay, so or volumetric analysis. Okay, so macro analysis deals with lots of volume or mass. Okay, so it we can use classical methods here, such as gravimetry and titrimetry. Okay. However, as your sample size decreases, then you have to adopt with newer methods. Okay, so you have to use newer methods that is only applicable to that quantity of sample. Okay. Okay, so if we lower down the sample size to 0.01 to zero point 0.1 grams or 0.01 ml to zero point 0.1 ml of your sample, then you are going to do semi-micro analysis now. The classical methods may not be good enough for semi-micro analysis because it could lead to lots of error when doing measurement. Okay? So when doing semi-micro analysis, you may want to do much sensitive techniques, no, so that so that you will be able to measure your substances, no, or your analytes. No, when we say analytes, that's the substance of interest. Okay, so that's the substance that you are analyzing. Analytes. Okay. If you go further down, okay, so if your sample size ranges from 10 raised to negative 4, that is 0.0001 to 0.001, I mean 0.01 grams, then you can do micro analysis. Okay. So when doing micro analysis, you should use more sensitive techniques, more sensitive apparatus, because again, the classical methods will no longer apply. Okay. And they are no longer applicable for very tiny amounts of matter. If you use a classical method such as gravimetry, titrimetry, it will cause lots of errors. No? So you can do electrochemical analysis or spectrophotometric analysis when dealing with very few samples. And the last one is when you have any samples less than 10 raised to negative 4 grams, then you must do ultra micro analysis. Okay. So what's the point of this slide? No? So the general point is that depending on your sample size, there must be a corresponding method for that. Okay. So if your sample size is very tiny or very small amount in amounts, then you must use much sensitive equipment, much sensitive apparatus when observing them. Okay. But if your sample size is big enough, okay, if you have plenty of your sample size, then you may do macro analysis, no, wherein the classical methods of analytical chemistry can be done. No? So, yeah. So as your sample size decreases, the technique must adapt to it. No? You must use better equipments when dealing with much smaller samples. Okay. Also, depending on the concentration of your analyte, the analyte is the substance that we are dealing with. Okay. Depending on the concentration of your analyte, we there is also a classification for that type of analysis na. So when your analyte concentration is around 1 to 100% of your sample, then the type of analysis that has to be done must be the major analysis or the major constituent analysis. Okay. Why major? Because uh, it predominantly it is the predominant substance in your sample. Okay, so that's a major analysis or major constituent analysis. However, if the concentration of your analyte decreases further, then we can classify them as minor analysis or minor constituent analysis, or if it is in ppb or ppm ranges, then we call it trace analysis, and anything lower than ppb will be considered ultra-trace constituent analysis. Okay, so again, depending on the concentration and the amount of your sample, there are um, there are certain methods that can be applied to them. Not all methods will apply to all. Okay, so if you have bigger sample or higher concentration, then you may deal them with classical methods. However, if the concentration or the amount of your sample decreases, then you have to adapt with something that is sensitive, no? Sensitive enough to detect the analytes. Okay, so yan. Okay, when doing chemical analysis, again, you only have to get the representative fraction. Okay, so for example, again, if you are observing the blood chemistry of a person, you're not going to get all the blood of that person, diba? Because it will die. What you want to do is just to get a few ml of that blood, and you're going to analyze it with, let's say, chromatography apparatus, instrument, no? Chromatography instrument to detect the concentration of your analytes in the blood sample. Okay, so again, we call it the representative fraction when we only get few portions of the population. Okay, so we only get few amounts from the original sample. Okay, and that is important in sampling. Okay, so the progression of the amounts of your substance that you are dealing with the laboratory are the following. Okay, okay, so there is a sampling increment. So that means as you go to your laboratory, your sample size decreases further. So for example, if I am going to analyze the Pasig River, which I did before, um, we went to the Ilog Pasig, and then we get at least 1 liter solution from that Pasig River. Then later on, when we are going to do chemical analysis in the laboratory, you're not going to analyze the entire 1 liter bottle. Okay, so you are only analyzing just a few portion of that. No, I think 5 ml lang yun. Okay, so that means every time you before you go into your laboratory analysis na, the sample size has been reduced significantly, and that's okay lang, okay? Because you're not going to analyze all of them naman, no? Your gross sample. You are not going to analyze all of them. You're just going to analyze the representative of that sample, okay? So that's why homogenization is important in Anachem because um, you want to make your solution homogeneous so that whatever your measurement is from your laboratory sample, that will be representative for your gross sample and as well the entire population. Okay, so that's how we do analysis. Okay, so for example, in doing blood chem, for example, you already have a 5 ml vial of blood. You're not going to analyze all of that 5 ml. No? You're going to pipette out just a few ml from that sample when doing analysis. Okay, so you're not going to use whatever you collected from the person. Urinalysis is the same. No, suppose they gave you this 10 ml or 20 ml bottle of urine, you're not going to analyze the entire volume. Okay, only a few portion will do. Okay, so that's how uh, that's how the progression of your sample size is when doing chemical analysis. Okay, so you started with a very big amounts. Okay, that's the population. You decrease it to the gross sample. Okay, let's say a few ml or liters, then later on you will further reduce the amount into a workable volume in the laboratory. Okay, then after gathering your sample, then we should know the standardization and calibration technique na, in order to measure the analyte levels in your sample. Again, when I say analyte refers to the substance that is being analyzed. Kaya nga analyte tawag. Okay. So again, substance that is being analyzed, we call them an analyte. Okay. So when we are going to observe the amounts of our analyte in our samples, then it is important for us to do the standard calibration or standardization and calibration. Okay. So when we say calibration, uh, in this sense, no, calibration refers to the establishing of relationship of the instrument response with the concentration of your analyte. No? So depending on the response of your instrument, you can infer the concentration of your analytes in there, because analytes, you do not know what their concentrations is, pero but you can determine them using instrument response. No? For example, we have here the copper analysis. Okay, so as you can see here at the top picture, so the concentration of copper actually increases here. Okay, on the leftmost side, you do not have any copper solution here. However, as you go to the right, the copper solution increases. Now, if you use your instrument to read the concentration of copper, this will be the result. Okay, this is called the standard curve. Okay, so the standard curve tells you the instrument response depending on the concentration of your standard. When you say standard, these are solutions with known concentration. Okay, we will discuss more of that when we are in titration na. Okay. So again, the solutions are called the standard solution because their concentrations are known. Okay. So when we analyze them using, let's say, UV-vis, okay, ultraviolet visible spectrophotometer, if we analyze this standard solutions with UV-vis, we will get instrument response. No? So, and the instrument response is proportional to the concentration of your substance. So if you plot the data, you will come up with a line. Okay, with a line. Okay. So for example, for this solution, it has no copper, so that means it must have no response from the instrument. Okay. If it has, then you have to correct for that. No, you have to subtract the uh, instrument reading for the blank. Okay, the blank is the solution without any analytes in there. Okay, so it's just water. So let's say this solution is 0.0015 molar in concentration. So if this solution is 0.0015 molar in concentration, then it must have an instrument response. No? So its y-axis will be increased. No? Let's say the y-axis for the instrument response is 0.05. Okay. And so on and so forth. No? So when establishing this standard curve from your standard solution, the instrument response must increase with the increasing concentration. Then, after you establish your standard curve, which is this one, you can now determine the concentration of the analytes in your sample. Okay, suppose I have this sample with a known concentration of copper. So after I ran my analysis in the UVVs, my instrument told me that the the response is somewhere here. Okay, the instrument response is somewhere there. Okay, okay. So what I want to do is that since I already know my instrument response, then I can compute for the concentration of copper from my solution. How? You're just going to extrapolate data. So this equation can be expressed in linear equation or y equals mx plus b. Since you already know the value for y or the instrument response, then you can solve for x, that is the concentration. Okay. So again, this equation can be expressed by linear equation. Okay, y equals mx plus b. You already know the instrument response of your analyte that is equivalent to y value. Then you can manipulate the linear equation to solve for x. Okay, you can extrapolate the data that will tell you the concentration corresponding to that response. Okay. Suppose you do another chemical analysis with another sample and the response is somewhere here. Okay, so that's the instrument response. You can also extrapolate the data by using y equals mx plus b. You solve for x because y is already given. Okay, so y is the instrument response, the x will represent your concentration. So uh, you can solve for x with that. Okay. So that's how we do chemical analysis now. So again, so the first thing you want to do in the laboratory when doing analysis is to establish a standard curve. Okay. So when establishing a standard curve, you must have solutions of known concentration. Then you you get their corresponding instrument response. You will come up with this linear equation here. and then you will use that linear equation to interpret the instrument reading from your analyte, no? The instrument reading of your analyte, no? So that you will get the concentration or the corresponding, yes, the corresponding concentration of your substance. Okay. Okay, so this technique is called the external standard calibration technique. No? So when we are doing external standard calibration technique, we use standard calibration curves, no, to determine the concentration of your analyte depending on the instrument response. No? So whatever I have discussed earlier, we call that the standard external standard calibration. Okay. It makes use of the calibration function or the standard calibration curve or the line, the equation of the line, to get the concentration from the response of your instrument. And this is very used in all analytical chem labs because number one, it's easy to do. Okay, madali lang siya gawin. Okay, you just set up your samples, you run it with your instrument, and then you analyze your analytes, then you're done. Okay, very easy technique when analyzing the concentration of our samples. So the other term for the standard calibration line is the calibration curve. Okay, so the calibration curve is an equation that that shows the response of the instrument depending on the concentration of your analyte na. So yun lang. And you can also use this to predict the concentration of an unknown analyte solution by extrapolating the data from the linear equation. You can solve for x with that. Okay, so that's how we analyze our analytes. When doing chemical analysis, you must minimize the errors. No, for example, you are going to analyze blood. Okay, you're not you're when analyzing blood, you're going to put that in a gas chromatography instrument. However, you must pre-treat your blood sample. Okay, because when you place the red blood cells in there, they may block the chromatography instrument, so it will be damaged later on. So you don't want that to happen because gas chromatography instruments cost around 5 to 10 million pesos. Okay, so they're very costly. So when you are using them, you must pre-treat your samples. Okay, so that your working liquids, no, your working solution will not destroy your instrument. And also, other than having your instrument working well, is that you will have good response from your instrument. Okay. Another example would be my Ilog Pasig experience. No, so when we are analyzing Ilog Pasig water, uh, your sample you your sample usually contains dirt from the river. No, sometimes it may have plastic plastic material in there. No, you don't want those plastic materials to be sucked up by your instrument, and then later on it will be blocked, no, and the instrument will be destroyed, no. So you don't want those things to happen, no? So for you to minimize errors, there are some methods that can be done to minimize them. Okay, so number one is the separations. Okay, so mechanical separation. So this is a this is a process, or this is a technique in which you separate heavier materials from your solution using filtration or centrifugation. Okay. So for the Pasig River solution that we obtained before, we filtered it using filter papers. Okay. So that the plastic materials, the soil, whatever is in there that is heavy enough, no, or thick enough to block with to block the instrument. So yun, we filtered them so that they will be removed, no, from our sample. Okay. Yung mga plastic, yun. Filter mo sila para ma-remove sila. Okay. So for blood analysis naman, you may want to centrifuge your blood first before you analyze them. Okay. Centrifugation will allow the separation of heavier molecules from the lighter molecules. No. Okay. So yan. So your blood cells will settle down at the bottom, and then your plasma will be left on top. No. So you can do analysis with the plasma. Okay. So other techniques involve precipitation, dialysis, solvent extraction, volatilization, ion exchange, and chromatography. No? So for example, you're going to analyze a plant, no? A plant extract. When dealing with plant extract, you must do chromatography first so that your sample, your laboratory sample, or your working, ay, ang tawag dun, your workable laboratory sample will be pure enough, okay? Because plants contain lots of materials, di ba? So when doing chromatography, you will pass through your extract, your plant extract. Y- You allow you allow your plant extract to be separated by polarity, and then you will collect the volume when doing chromatography. So yan, your analytes will be concentrated later on. We will discuss that on the last chapter naman para clear. Okay. So the chromatography stuff will be discussed in the last chapter of this semester naman. Okay. So yan, let's leave that hanging na lang. Okay. So yan. So that's how separation works. So you filter out anything that may interfere with your analysis so that your instrument will not be broken, and then you will have good instrument response. Okay. So you filter them, or you separate them so that yun, you will have good measurements with your samples. Next one, the next technique to minimize the errors in your laboratory samples would be saturation and matrix modification. When we say saturation, it is it is about concentrating your analytes in your sample. Okay, so for example, you have certain volume for your solution. Okay, you may want to reduce the amount of water by boiling the water off. No, so when you boil off the water, the volume of the solution will decrease, and as a consequence, the concentration of your solute will increase. No, and that's saturation um, of your solution. Okay. Sometimes it may involve addition of interfering species so that the interference will be independent from each other. No? Because interferences may ano tawag doon? Ayun. So, interferences may interfere with the analyte response kasi. So, sometimes you may want to add more interferences so that their concentration will be significant enough to be detected and later on to be removed from the measurements. Okay. So, that's saturation method. Another method is the matrix modifier. Matrix modifier, this is a substance that is added to your solution in order to suppress the amount of your analytes. I mean, the interference pala. Okay. So these are solutions that help to remove or to help minimize the response of your interferences from your analytes. No? So one example of which is when doing blood chem. Okay, so if you do not want other ions to be detected in your blood, then you have to add masking agents or matrix modifiers so that their concentration will not show up when doing analysis. Okay, so a friend of mine analyzed blood samples from the incident in one school here in the Philippines wherein the mercury leaked, no, and then this people or these children actually got mercury from that leak, no? So she was the one to measure the lead content of the blood, no? So according to her, before she analyzed the blood, she centrifuge it, no? And then she just obtained a few amounts of that blood sample. She added matrix modifier so that other ions in the blood will not be detected, no? Because other ions can be detected as well other than lead. That is the focus of the experiment, no? So sodium can be detected, potassium can be detected, other anions can also be detected, so that you have to add the matrix modifier so they will be masked, no? So they will not show up when doing analysis. Okay, so yeah. And then the last technique is the dilution and matrix matching. Okay, so dilution can be used when your interferences are significant in instrument responses, no? Kunwari, yung when you're doing measurement, the instrument detects your interferences, then you can use the dilution method. So what's dilution method? When doing dilution method, you just add water to your sample so that the concentration of your interferences will decrease. So, and because the concentration of your interferences decreased, no, the instrument the instrument response for those ions that are interference, no, will also decrease, no, leaving your your analyte, no, your desired substance, the only thing that is readable by the instrument. Okay. So again, dilution method is when you add water to your sample in order to decrease the response of the instrument to your interferences, no. So you so yan. Okay, excuse me. So again, dilution method, you add water to your sample so that the concentration of your interferences will decrease, leaving only the analyte, no, the readable substance in there. Okay, and the last one would be matrix matching. Okay, so matrix matching is is an attempt to duplicate the sample matrix by adding major matrix. So basically, it just tells us that uh, when you're going to do matrix matching, you're let's say you run your sample and you get data from your interferences. Now, so what you're going to do is that you will duplicate whatever the concentration of them of those interferences are now. So you're going to duplicate the concentration of the interferences, and then you will rerun your sample. Then later on, whatever your interference concentration is, you will deduct them from the matrix match. Okay. So, kumbaga, you will just subtract the the sample reading with your matrix match reading. So when you subtract the two data, you will be left with just the analyte data or the analyte reading. No? So that's how we do matrix matching. So again, when doing matrix matching, you are going to duplicate the matrix concentrations. That means the concentration of your interferences. And then you're going to run your sample, and you will deduct the concentrations of your interferences so that you will be left with your analyte concentration na lang. Okay. Okay. So, yan. Okay. So, you will learn more of this naman when you work in laboratories na, no? Because working in lab will make make these things clearer, no? Pero whatever I told you earlier, yun yung mga ginagawa talaga, no? So those are the stuff that we really do in labs, no? So yan. Okay, my favorite technique here is this one, separations, because it will just involve filtering stuff now. Okay, and then yeah, yung other methods dito, these are things that uh, are time consuming, no? So yun. So I do not use them all the time. Okay. Yun lang naman yung kwento dito. Okay, so let's proceed with the next one. Last Earlier we have the external standard calibration. So if you could still recall, external standard calibration makes use of standard solutions, and then you will graph the instrument response per concentration of your solution. So you will establish this calibration curve. No? This calibration curve is this linear graph here. Okay. You will use this line in order to obtain the concentration of your analyte. No? However, we can also do other techniques, no, to determine the concentration of your analytes. No? Other than external standard calibration technique, there are other techniques that can be done, such as the internal standard methods. Internal standard methods involve the use of standard solution or your reference solution. You will add that solution in your sample so that they will also be read by the instrument. Okay. So suppose we have this chromatogram here. So in these graphs here, no. So what happened here is that this is our sample, okay, and then we have the analyte here, the analyte reading here, which changes. However, your internal standard solution has a constant reading. Okay. So in order for you to determine the concentration of your analyte, you may want to do ratio and proportion with the internal standard. Okay. So you're going to get the ratio and proportion of the internal standard for each reading. Okay. So when you establish the correct proportion, then you can solve for the concentration of your analyte. Okay. So we have here an example. Okay. So this is used when detecting sodium from the liquid solution. Okay. Sodium, when detecting sodium from liquid solutions, it is quite hard because there are many interferences. Okay. Other than sodium, magnesium, calcium may be present in your solution. So what the analyst did here was um, nawala. Okay. So what the analyst did here was that um, after he detected the sodium intensity according to the instrument response, no, or the sodium instrument response here, he also determined this lithium response from the instrument. Okay, so depending on the concentration of the lithium and the sodium, there is a corresponding instrument response from that. So the lithium served as the internal standard. So this is something that is fixed, no? Okay. Na this is something that is added to the solution in fixed amounts. So he can establish the ratio and proportion of the two substances. Okay. So on the last column, we have here the ratio of our two substances, and whatever that ratio is, that is used to determine the concentration of the unknown. Okay. So again, when we say internal standard method, what we're doing here is that we are going to add fixed amounts of our internal standard or reference substances. Okay. So when you say internal standard, again, standard are solutions with known concentrations. Okay. So you add your internal standard in your sample, and then you read your analytes, and then depending on the instrument response, you can get their ratio and proportion so that you can determine the uh, concentration of your analyte in the unknown sample. Okay. So, ano, that's quite different with, ano, ha? It's quite different with this technique, this external standard calibration, because what's the difference? In external standard calibration, you set the calibration curve with external standards. Okay. Why are they called external standard? Okay. Number one is that, or the only reason for calling them external standard is that you do not add them in your sample, hence they are external. Okay. However, for internal standards, you add them to your sample. So they are called internal. They are inside the sample kasi, no? So that's the difference, no? You also establish calibration curves, no? So ganun. But the only difference is that the calibration curve for external standard is done before analyzing your sample. For internal standard calibration, your calibration curve is done when you analyze your sample together with your reference solution or your standards. Okay, so that's the difference between the two. Okay, again, external standard, you analyze you establish the calibration curve of your standard solution first before you analyze your sample. For internal standard methods, you analyze the substance, your analytes, and your reference materials at once. Okay, you analyze them both at the same time. So that's the difference between the two. And the last technique is called the standard addition method. Okay, so standard addition method involves the addition of a standard with your solution. Uh, in this process, we do not have to establish the we don't need to establish the calibration curve na. Okay. So there is no need to do calibration curve here at most. Okay. Sometimes it may require, but most of the time you will not need the calibration curve. Okay. So what happens here with standard addition method is that you add your standard solution with your unknown solution. Okay. So depending on the ratio of the response of your sample, again, you will do ratio and proportion just like the internal standard solution. So you will do ratio and proportion with the response of the instrument with your unknown solution and your substance with or your sample with standard addition. Okay, so you're going to compare the two readings. Okay, so the one without this standard and the one with standard, you're going to compare their ratio. Okay, the instrument response ratio, so that you will be able to determine the concentration of the unknown. Okay, so ganun lang. So again, standard addition method involves the use of standards being added to your unknown solution. And then what's next, that you're going to analyze your solution alone and the unknown solution with the standard. Okay. So the two will have different responses. No, they will have different instrument response because the concentration of your unknown uh, changes. No, because of the introduction of the stock or the standard solution. No. So yan, by determining how the ratio of their instrument response, you can determine the concentrations of the analytes in there, no? so so all of these techniques in analytical chemistry, they all make use of the ratio and proportion lang, no? And sometimes equation of the line. Okay, so for external standard calibration, you make use of the calibration curve. for internal standard methods, you also use calibration curve. However, for standard addition, you make use of ratio and proportion lang. Okay, so you only use ratio and proportion for this technique. Okay, so yun. And lastly, this let's talk about the figures of merits in analytical methods. Okay, so what are the figures of merits? So they just describe how efficient your method is. Okay, okay, so one of the figure of merit when doing analytical techniques is that you have to determine the sensitivity of your calibration curve. Okay, the sensitivity of your calibration curve depends on the slope of the curve. No? Asan na ba yun? Okay. So again, the sensitivity of your calibration depends on the slope of your curve. No? There are three types of curves, or there are three. Ayan. There are three common curves that we encounter when establishing calibration curves. No? The one having a slope that is high, okay, so but not equal to 1, okay, so we have this steep slope here, okay, and then the other one has a normal slope. If you obtain the angle using trigonometry, the angle would be around 45 degrees. And we also have a calibration curve in which the slope is very low. Okay, so this. Okay, so these are the three usual appearances of the calibration curve. One is the steep one. The other is the normal slope. Okay. Okay, when you say normal slope, the angle of the calibration curve is about 45 degrees or so. And then the last type of the calibration curve is the one in which the slope is very low. Okay, so that means there is a very slow change for the y-axis. However, your x-axis changed a lot na, no? Okay. So depending on how your calibration curve looks like, you can determine its sensitivity. The one with the steepest slope is the most sensitive. Okay. Why is this the most sensitive? Okay. The reason why this is the most sensitive is that um, with just only few changes in your x-axis, or let's say the concentration axis, there will be a huge change in your y-axis. Okay, so this steep slope, or this type of sensitive calibration curve, can be used when dealing with trace analysis or ultra trace analysis. Okay, so you can use this when analyzing trace or ultra trace constituents, okay, in your sample. Because again, trace amounts, ibig sabihin nun, onti lang yung concentration. So when doing trace or ultra trace analysis, you are dealing with just few concentrations of your sample, and you want your instrument to be sensitive enough to detect them, so that the resulting calibration curve will look like this. Okay, the slope will be very high. Okay, so this is suitable again for trace and ultra trace analysis. However, for other types of analysis, let's say minor or major constituent analysis, this will not work very well. Okay. So for using when you are going to analyze your minor or major constituent, no? So you may want to use a calibration curve whose slope is just okay, so the slope is just around 45-degree angle. Okay. Again, this one is sensitive enough to be used in trace and ultra trace analysis. This one can be used for my minor and major constituent analysis. Okay. The last one, we do not use this at most because the instrument, when you have a slope that is very low, that means your instrument is not working that it's not working well. No? So that means you have to check your instrument whenever you see a slope with this appearance. Okay. So you may want to check your instrument whether there are issues with the light source, or there are issues uh, s- with the injector. So yun. So whenever you see slope like this, that means you have to check your instrument if it's working well or not. No? The acceptable curves are this one, the most sensitive one, and this normal curve here. This one, not much. Okay. Okay. So, yan. So that's one of the figures of merits. No? So, yan. We have the calibration sensitivity. So, depending on the slope of your calibration curve, the sensitivity changes as well. Okay. So, if your slope is high, then that means the the calibration curve is sensitive towards few amounts of substances or few increments of your substances. However, if your calibration curve has a low slope, mababa yung slope niya. So that means the instrument isn't that responsive with the concentration of your analytes in the solution. Other figures of merits are the following: the detection limit and the linear dynamic range. Okay, so let's talk about the linear dynamic range first. Okay, so suppose we are going to do external standard calibration. So at first, you will observe that the instrument response and the concentration of your substance will be linear at first. However, as you go, as your concentration go higher, the instrument response may plateau. Okay, so that means it may flat out at the end. Okay, so it may flat out or it may plateau when your concentration is very high. So ayan. So if that happens to you, this usually happens at higher concentration, wherein your instrument response deviates from the linear curve. No, when it started deviating from your linear curve, that means the instrument the cannot read the concentrations higher than the last point in the linear curve. Okay, so that means your analysis has only ay ano yun, nawala ako. Okay, ulit tayo, nawala ako eh. So that means, no, when when your data points deviate from linearity already, that means your calibration curve has a limit, no, and the limit is where the last linear point is, no. So for example, this is the last point where the linearity can be established. So that means your analysis can only be done at this range na lang. Okay. So anything beyond that may give you unreliable results na. Okay. So that means when doing analysis, your ranges can only be somewhere in here. Okay. So at the beginning and at the end of the linear point. Okay. So yan. Kasi again, usually at higher concentration, the instrument response deviates from linearity. You don't want this data to be read, no, by your instrument na, because the instrument is not reading them well. Okay, so yun. So if the instrument cannot read your concentrations very well, then you have to establish a limit. Okay, so that means you have to set a limit for your calibration curve. Okay, any concentrations higher than your limit may give you bad results. Okay, so that's the detection. That's the linear dynamic range pala. No? When you say detection limit naman, again, the linear dynamic range tells you where the concentrations are ano are good with the instrument response. No, anything beyond that that may give you unreliable results na. Okay. So the detection limit naman is the lower limit. Okay. That is the lower limit of your calibration curve. Okay. So remember that in all measurements there is called a relative I mean there is called a random error, 'di ba? And random error can be determined using standard deviation. Okay. So you do not want any measurements or any concentration below your standard below your standard deviation nga. Okay. Why, Kasi when we say standard deviation, these are the noises in measurement na. So those are data that cannot be interpreted because they are errors, no? They are errors technically speaking. Okay. So you do not want any concentrations lower than your standard deviation so that whatever your standard deviation is, that is also your detection limit. Okay. So that's the lower end of your concentration dapat. Okay. So again, when establishing this curve, you must check. Okay, you must check where the linearity ends. Okay, when your data point started to plateau, okay, you may want to remove that part wherein the plateau will start. Okay, you may want to remove this in order to make your line if in order to make your linear equation. Kasi if you include these two data, then the linearity of your line will decrease, no? Or if you could still recall your statistics, that's called the Pearson correlation coefficient, diba? So if you include these two data points here, the Pearson correlation coefficient of this line will decrease. So that means your calibration curve is unreliable. So in order for you to have a reliable calibration curve, you will remove the data points where it deviates from the linearity. Okay. So after establishing your linearity, you may want to obtain the standard deviation of the curve. Okay, whatever your standard deviation is, that will correspond to the detection limit. So any concentration lower than the standard deviation is not good. Okay, so that you will not get reliable results with that now, because again, when I say standard deviation, these are results from random errors or other types of error in your analysis now. So that means any concentration lower than this, that will give you false positive results, pwedeng ganun. Okay, any concentrations higher than your last point naman, that will give you unreliable results as well. Okay. So that's why you have to take note of the calibration curve parate. Okay. And that's all for today. So let's sum up whatever we have discussed today. Tapusin na natin to. Let's summarize whatever we have discussed. So, excuse me. So let's summarize. So again, when doing chemical analysis, we are not going to analyze the entire population. Instead, we will just get the representative of that population, and that's called sampling. Okay. Depending on the concentration and the amount of your substance, you can have different types of analysis for that. Okay, so that means you have specific analytical methods to be considered depending on the amount of sample and the concentration of analyte. Okay, so macro analysis deals with sample sizes that are quite big. However, if your sample size decreases further, then the type of analysis will change. Okay, ultra micro analysis being the type of the analysis that will deal with very small uh, amounts of your sample. Okay. Also, depending on the concentration of your analyte, you can have different types of constituents analysis now. So if your analyte concentration is around 1% to 100%, then that is a major constituent analysis. However, if the concentration of your analyte decreases, then the type of constituent changes now from major to minor trace and later on to ultra trace. So ito lang din yung sa first slide. So again, the process in which you get a representative from your population, that is called sampling. Okay, and when you do chemical analysis in the laboratory, your sample size decreases further to something that is workable in the laboratory. Okay. So again, when you collect your gross samples, you're not going to analyze all of them. You're going to analyze just few of them now. Okay. When analyzing the concentration of your analytes, you may want to do the standard and calibration, okay, or the standard calibration technique. So calibration, that means you are establishing the relationship of your instrument response with the concentration of your substances. No? So once you establish the relationship between the two, the instrument response and the concentration of your substance, then you can come up with this curve. We call that the calibration curve. Okay. There are several techniques when establishing standard calibration. One is the external standard calibration, in which you use external standards in order to obtain the calibration curve. Okay, and then you will use the calibration curve to identify the concentration of your analyte. Okay. Other techniques involve the use of internal standard method. Okay. Internal standard method refers to addition of your standard inside your analyte solution. Okay. So depending on the response of the instrument of your analyte and this internal standard, you can obtain the ratio, and then you can use the established calibration curve from that ratio as your basis for analysis, no, or as your basis for determining the concentration of your analyte. Okay, and the last one is called the standard addition method. This usually do not require the curve. It usually don't require the standard curve. You're just going to do ratio and proportion here. So when doing standard addition methods, well, the first thing you're going to do is to get your unknown solution. Okay, so get your analyte solution, obtain the reading from that, and then later on, you will add a standard in your unknown solution. Okay. So a standard is a solution with known concentration, right? So that means when you add this standard concentration into your unknown solution, then the concentration reading must change. Okay. So depending on the changes of the reading of your analyte, then you can do ratio and proportion to determine the original concentration from your unknown solution. Okay. And then before you do analytical procedures, you may want to minimize the errors first. Okay, so errors, this may result to lower precision or lower accuracy of your analysis. So um, in order to increase your precision and your accuracy, you have to remove the interferences. Okay, or those when you say interferences, those are the stuff that may give you bad reading for your uh, data analysis. Okay, they may give you bad measurements. Okay, so in order to minimize the errors, you may do separation. Separation involves the use of different techniques in which you're going to separate out other unnecessary particles, no, other unnecessary substances from your analyte, no. So that's separation. Next one is the saturation. When we say saturation, that means you're going to add interferences uh, to your sample so that you can detect them, and then later on you can remove those readings. Okay. Matrix modifier is the counterpart in which you add this matrix modifier solution in your sample in order to suppress uh, your interferences from being read by the instrument. Okay. So again, they are two counterparts. No? Saturation involves the addition of your interferences so that they can be read, and then later on you can deduct uh, whatever the reading of your interferences are. So you will be left with your analyte alone. Okay. For matrix modifier, you're going to suppress the interferences so that your instrument will read the analyte only. Okay, so there are two contrasting methods now. And the last is the dilution method and the matrix matching. So when we say dilution method, what you're going to do here is to dilute your solution further so that the interferences can no longer be read by your instruments. Okay, your analyte concentration may decrease. However, you can do ratio and proportion depending on the amount of water you added. You can use the dilution formula. M1 V1 equals M2 V2. You can use that no, to determine the original concentration of your analyte before you diluted your solution. And then the last one is the matrix matching. What we do here is that we duplicate the interferences so that we can deduct them from our measurements of the sample later on. So that is something similar to the saturation method. No? Okay, so for matrix matching, you're going to duplicate your matrix. It means you're going to duplicate all the interferences, and then later on, you're going to deduct them from whatever is in your sample. Okay, so that you will be left with your analyte measurements na lang. Okay, and then lastly, the last one describes the calibration curve. Our calibration curve can be described by different figures of merit. No? So when you say calibration sensitivity, that pertains to the slope of your calibration curve. If your calibration curve has a very high slope, then it means it is very sensitive. No? And that is good when you are doing trace and ultra trace constituent analysis. However, you may want uh, a lower slope, no? That means a slope around zero point 0.5, no? The usual 45-degree angle slope, no? So you may want to use that when doing major and minor trace analysis. If your slope lower if your slope is lower than the 45-degree angle, that means masyado siyang mababa, okay? So if your slope is very low, that means there is something wrong in your instrument. Then you have to check, no, whether your instrument is working well, or is it calibrated before use, no. So yun. So that's calibration sensitivity. That can be determined by just looking at the slope of your line. The detection limit is the smallest concentration that can be read by your instrument, and it is equivalent to the standard deviation of your curve. Okay, so the standard deviation of the curve can be obtained using some statistical tools. No, so after determining the standard deviation, uh, you will let that standard deviation be equal to your detection limit. That means any concentrations lower than this cannot be considered significant. No, so you will treat them as noise or errors. Okay, so anything lower than your detection limit or the standard deviation isn't a good measurement. Okay, that they will not give you reliable results. No? So also, when you increase the concentration further, the linearity changes to to a plateau curve or hyperbolic curve. No? Nagiging hyperbolic curve yan. So in those cases, no, when your curve starts to plateau, okay, so when your curve starts to be hyperbolic, you may want to remove those points at the end in which they start to deviate from your linearity, so you may want to remove this stuff because again, that means that your instrument isn't reading the higher concentrations very well, no? So you may want to remove them, and that means you have to establish the upper limit of your measurement. Okay, so the upper limit usually corresponds to a few notches after the last point, no, of your standard calibration curve, no. Okay. So yan. So that's all for the chapter 2. So that means your quiz will be um, um, walang there will be no calculation in your quiz. So quiz 2 will be a lot easier than quiz 1. Okay. However, the quiz 2 could be it could be identification, although multiple choice type, and sometimes there will be questions that will involve analysis, no. So ganun, case to case basis analysis gagawin natin sa quiz. Okay, so that's all for chapter 2. By next week will be FEU founding anniversary week, no. So there will be scheduled activities next week. um I don't know if there is a schedule for Friday. I don't know if you will be excused next week, no. So please check the ano na lang, please check the central student organization post, no, regarding the student activities for next week, no. If ever if ever we're not suspended next week, Friday, we're going to proceed with chapter 3, and that will be equilibrium equations, and that chapter will be good for 3 weeks. Okay, so please be prepared for that topic. No? So medyo mahaba yun eh. Okay, so okay, so that's all for today. So thank you for attending the class. A copy of the class recording will be uploaded tonight, no, on YouTube so that you can review that when taking your quiz. No? So yan. So thank you and stay safe as always. Okay. So bye bye.